Let's talk about the structure and chemistry of the Earth, and we'll focus on the chemistry of Earth's mantle and crust. So the early Earth formed at around 4.7 billion years ago, and the process involved planetesimal accretion that led to a homogeneous and dead planet. Protoplanet Earth grew over time from a barrage of extraterrestrial impacts, increasing its mass with each bombardment. As the protoplanet grew in size, it increased its gravitational field and would have attracted even more objects to its surface. And the colliding bodies included metal-rich fragments, so iron meteorites, rocky fragments like stony meteorites, and icy fragments like comets. The impacts became increasingly violent as Earth's mass and gravitational field increased, causing the initial rise in Earth's internal heat. Radioactive decay processes released heat in Earth's early stages of formation, and the young Earth had a greater complement of radioactive elements. But many of these, for example, aluminum-26, are short-lived and have decayed to near extinction. Others, with a more lengthy rate of decay, are still undergoing this radioactive process, and so still releasing energy in the form of heat. The greater heat content of the early Earth was a product of 1. A greater abundance of radioactive elements, 2. A greater number of impacts, and 3. The adiabatic heating, that is, heat generated by the compression from overlying rock. And if we look at just a temperature profile through the Earth, we see that temperature increases as you go deeper down towards the center of the Earth. This is, in part, adiabatic heating. And I put in here a glowing red-hot pellet of plutonium-238 dioxide that was used in a radioisotope thermoelectric generator for either the Cassini mission to Saturn or the Galileo mission to Jupiter. The pellet is glowing red because of the heat generated by radioactive decay, primarily alpha decay. So, in the early Earth, we had this rather homogeneous sphere composed of fragments from these impacts, but the increased heat content of the Earth resulted in melting of Earth's interior, and the planet became density and compositionally stratified, with the denser metallic materials sinking to the center of the Earth and the more buoyant rocky materials floating up toward the surface. The core is overall larger than Mars, which is about 1/6 the volume and 1/3 of its mass. The inner core has pressures more than 3 million atmospheres and temperatures in excess of 6,000 degrees Celsius. It's about 70% the size of the Moon. And the core is mostly metallic iron with some nickel and silicon. And of course, the outer core is molten and the inner core is solid. The outer core is so hot that the metal is always molten, but the inner core pressures are so high that they suppress melting, even though temperatures there are over 6,000 degrees Celsius. The outer core ranges from about 4,400 degrees Celsius near the mantle to over 6,000 degrees Celsius near the inner core, and ranges from about 2,900 to a little over 5,000 kilometers depth. The outer core is molten, and because the Earth rotates, the outer core spins around the inner core, and that causes the Earth's magnetism. Here are examples of an iron meteorite and a chondritic meteorite, and these meteorite compositions tell us about the chemistry of the early universe and about Earth's core and mantle. Most of these meteorites are originating from the asteroid belt, but many are also being identified from the Moon and Mars. If we look at the composition of these meteorites, the iron meteorites are, of course, comprised of metals, but the chondrites, those rocky meteorites, look a lot like mantle compositions with nickel and iron. They include enstatite, olivine, bronzite, which is the magnesian end member of orthopyroxene, hypersine, which is just intermediate composition, orthopyroxene, and serpentine. We know this from the meteorites that we find on Earth. And just notice that it's the iron meteorites that we find a lot of because they are so different from the rocky or the chondritic meteorites that look like normal rocks on Earth. Considering the abundance of elements in the solar atmosphere and elements in carbonaceous chondrites, you'll see there's a one-to-one correlation with this slope, indicating that the carbonaceous chondrites are very similar to the elemental composition of the solar atmosphere. And so these are good estimates for early Earth. The mantle is about 80% of Earth's volume, and it's primarily magnesium and iron silicates, and it's got several discontinuities within it, and across those discontinuities, the atomic structures of the minerals that are in the mantle are compressed into denser structures because of the great pressures in the mantle. We can distinguish the upper mantle from the lower mantle at a seismic discontinuity at about 660 to 670 kilometers down. And that is where we're going from an upper mantle that is comprised of minerals like olivine, pyroxene, garnet, and spinels, corresponding to rock types like dunite, peridotite, pyroxenite, to the lower mantle composition that is comprised of compressed iron and magnesium silicates and lacks the tetrahedral coordination in those minerals because their structures change at that discontinuity. And we don't have any exposed examples of lower mantle rocks on Earth. We can estimate the mantle composition in several ways, and we do this in part by looking at ultramafic xenoliths, stony meteorites, considering the geophysical requirements for density and seismic velocities in the mantle, estimating from heat production from the decay of uranium, thorium, and potassium. And basaltic magmas have to be able to form from partial melting under mantle pressure and temperature conditions. And so oftentimes we use this model of pyrrolite, which is 3 parts peridotite to 1 part basalt. And that's this model here in sample 1, which is ultramafic compared to basalt with less silica, more iron and magnesium, and more calcium. Other estimates rely more on meteorites or on undepleted mantle using a layerzolite composition. We have direct evidence of mantle composition from ophiolites, which are pieces of oceanic crust and upper mantle that are scraped onto the continents at subduction zones. We also have dredge samples from oceanic fracture zones, nodules and xenoliths in some basalts, or that come up even in granite batholiths in the southern Sierra Nevada, for example. We also have kimberlite volcanoes that bring up xenoliths from the mantle. These are the diamond-bearing volcanic pipes that are erupted really rapidly. There are no modern examples, but we find them in South Africa, in Siberia, in Canada, and those bring up these mantle xenoliths with them. And we also have mantle samples from deep ocean drilling. Here are some examples of dunite, so these olivine-rich nodules in basalt that come up in Hawaiian basalts. Here's an example of a kimberlite volcano. It looks kind of like this. They don't have a surface expression like typical stratovolcanoes, but they are erupted from deep in the mantle. It's believed that they're erupted over a matter of days or even hours. They have a particular composition, minerals that include chrome pyroxenes and really magnesian garnets that look this bright pink. And they bring with them large diamonds sometimes, and that's why they're mined. And most of the diamonds that go into jewelry come from kimberlite volcanoes. Here's an example from Kimberley, South Africa, and it was mined in the late 1800s. And basically the structure of this volcano meant that they dug straight down into the diamond-bearing rocks. This is an idealized cross-section of an ophiolite that's based on the Samail ophiolite, which is found in Oman. And this is that part of an upper and lower oceanic crust and uppermost mantle that underlies the oceanic crust that was scraped onto the edge of a continent during subduction. So we have distinct layers that are found in a nearly complete succession in Oman, and elsewhere, like the Franciscan, we only see some parts, namely the upper part of the ophiolite sequence in the Franciscan, with the red cherts that we have on the north side of the Golden Gate, the pillow basalts, and those are associated with other rocks that were in the subduction zone itself. In the complete ophiolite sequence, at the top we start with the deep sea sediments, which could be cherts like we have in the Franciscan. Those represent, at least here, small ocean-dwelling animals that died and their shells or their tests fell to the seafloor and over time were lithified. Under that is the top of the oceanic crust, which is represented by pillow basalts. Under that is a sheeted dike complex. Beneath the sheeted dikes, you find the intrusive rocks of the oceanic crust. So gabbro, that here is broken down into a normal sort of gabbro that you see in a petrology class, which overlies a foliated gabbro. Under that is a layered gabbro, where we see earlier formed crystals of pyroxene, for example, perhaps some olivine near the bottom of these layers. And beneath that is the petrologic moho, and so separates the oceanic crust from the uppermost mantle. And so beneath the moho, we have ultramafic rocks like Harzburgite and Wherolite. So these ophiolite sequences are found either on the edges of continents or the edges of ancient continents that are now inland perhaps. And these are oftentimes associated with subduction zone complexes, which means that they're associated with high pressure, low temperature rocks like eclogite and blue schist that were subducted deep into the uppermost mantle sometimes. It was geophysics that was responsible for discovering a lot of the rheological and petrological transitions that we have in the internal parts of the Earth. And those include seeing an increase in the speed of seismic waves with depth because of the increasing density of those rocks in the mantle. And then we see sudden decreases in the velocity where we have rheologic changes in the Earth. For instance, this Gutenberg discontinuity occurs at the core mantle boundary. Because we have a liquid outer core, there is a sudden decrease in the velocity of the primary waves, the P waves, as they pass through the outer core. And the S waves disappear because they aren't transmitted through liquids. We see the P waves increase in speed as they pass to greater depths, and then drop in speed when they reach the core mantle boundary, moving from a liquid to a solid, and so the P wave velocity increases again. This is accompanied by an increase in the density of the rocks as you pass through the mantle and then across the core mantle boundary. And geophysicists used the way that these P and S waves pass through the Earth to detect different layers based on the differing speeds and arrival times at different locations around the Earth. And of course, the shadow that's created by the liquid outer core is what led to its discovery. We can look again at the Earth's structure to see the solid inner core of nickel and iron and some silicon, the liquid outer core that spins and gives us our magnetic field. I should say that the solid inner core also spins, and it actually spins faster than the Earth rotates. We have at the core mantle boundary the D double prime layer, which we'll get to in a moment. Then the lowermost mantle, which is comprised of minerals that have a much denser structure than the upper mantle, that transition from the mantle minerals like olivine, pyroxene, etc. Those mineralogic structures disappear at these discontinuities, and we have these petrologic transitions at 440 kilometers and at 660 kilometers. And then we're into the asthenosphere, which is the gooey layer of uppermost mantle that the tectonic plates ride over. And then on top of that, another solid layer of mantle, followed by the Earth's crust. So continental crust, which is much thicker, say 20 to 80 kilometers thick, and the oceanic crust, which might be 6 to 10 kilometers thick. And it's the crust and the uppermost mantle before the asthenosphere that comprise the lithosphere, that hard layer that form the rigid tectonic plates. The moho was discovered in between 1910 and 1912 by a Yugoslavian scientist after a large earthquake in Europe around 1906. The core mantle boundary, also called the Gutenberg discontinuity, was discovered by Oldham after a magnitude 8 earthquake in 1896 in Assam, India. And the inner core, outer core boundary was discovered by a female geophysicist called Lehmann, and that is named the Lehmann discontinuity, discovered in the 1930s, and she was a Danish scientist. Until the 1950s, the crust was synonymous with the lithosphere, and it wasn't until the mid-1960s that we started to understand plate tectonics. The 440-kilometer discontinuity is the depth at which we see a change in the olivine structure to a spinel or ringwoodite phase. And the 660-kilometer discontinuity is where we have a transformation of all minerals into a perovskite and minor iron magnesium oxide, so magnesium wüstite. And that 660-kilometer discontinuity forms the boundary between the upper mantle and the lower mantle. Now, this is a phase diagram down here to the right, where we see depth on the y-axis and mantle composition on the x-axis. And you can see the transitions at 440 from olivine and pyroxene to Wadsleyite and ringwoodite, followed by a transition at 660 kilometers to magnesium wüstite and magnesium perovskite. Let's look a little more closely at the phase changes that take place in the mantle. This graph plots depth from the surface down to 1,800 kilometers and density on the x-axis. The density overall increases in the mantle. The plot here starts in the mantle, and we see a low velocity zone just beneath the moho, where there's 1% partial melting. And the composition of the mantle at these depths is olivine, clinopyroxene, orthopyroxene, and pyrope garnet. That's the magnesium end member. Then at the 440 discontinuity, we see the loss of pyroxene and olivine. The pyroxene is transformed to a garnet structure, and olivine goes to a polymorph of olivine that's a denser structure at these high pressures. Then density continues to increase toward the 660 discontinuity, and we have spinel structures of the minerals here. At the 660 discontinuity, we have a loss of the tetrahedral structures, and so that is like the silica tetrahedra that is found in many of these silicate minerals. In the lowermost mantle, we see continued phase changes to these denser structures, garnet going to an ilmenite. Any silica is a stishovite, not quartz. And we see phases like perovskite form. The next slide will show you a bit more about that. These are the changes in the crystal structures as the mantle pressures increase. And on the top, I show you the olivine polymorphs. We're starting with forsterite, which is the magnesium end member. And with increasing pressure, we see the structure change. Notice that the magnesium oxide units are represented by the red, orange, and pink colors, and the blue colors represents the SiO4 units. And one thing you can notice in the olivine polymorphs is simply that the SiO4 units are becoming more densely packed in the ringwoodite compared to the forsterite. Down below we have the orthopyroxene polymorphs. Here's enstatite, and that transforms to majorite and achimotoite at greater depths. So these diagrams, they don't exactly show the size of these molecules decreasing, but if you look at the packing of various units within these models, you'll see that they are more densely spaced. Okay, and I want to make sure that you understand clearly that there is a compositional layering between the crust and the mantle, and that there's a thermal, rheological, mechanical layering that's described by the lithosphere and the asthenosphere. So on this figure, you see the compositional layering. Here it's labeled seismic layering, and on the right, the rheologic layering. And just notice that the rheological layering, you'll see the lithosphere is the rigid cap to the Earth, and it includes both the oceanic and continental crust, and the rigid lithosphere that is at the topmost part of the mantle. Beneath that, we have an asthenosphere that is partially molten and deforming plastically. And in the lowermost mantle, we have a rigid lower mantle. And the rheologic layering changes at the outer core where it becomes liquid. At this point, it is hot enough that it can melt that part of the Earth, and then of course the pressure overtakes the liquid outer core and transforms that to a solid inner core in the center of the Earth. Now let's look at the compositional layering. Compositionally, crust is distinct from the mantle. It has a very different composition. The oceanic crust is a thin basaltic layer. The continental crust can be anywhere from about 20 kilometers to, let's say, even 80 kilometers in the highest mountains, the Andes, the Himalaya. That is overall about andesitic. Beneath that, we have the mantle, which compositionally is iron and magnesium silicates. And I just described how their structure changes, but they're polymorphs of minerals that we are used to looking at, the olivine, the enstatite, etc. And then, of course, the composition changes again at the core, where we see metallic iron, nickel, silicon. This lowermost diagram shows the very thin oceanic crust, on average, let's say 6 or 7 kilometers thick, the continental crust, which is much thicker, but that the lithosphere includes both the continental crust and uppermost mantle, the oceanic crust and uppermost mantle, above the plastically deforming asthenosphere. So the tectonic plates are comprised of the entire lithosphere, not just the crust, and they are riding on the gooey asthenosphere. In the deep part of the mantle, we see the D double prime layer, and that forms at the core mantle boundary. The D double prime layer is considered to be primordial Earth that surfaces in hotspot plumes. So the D double prime layer is the origin of the melts that feed hotspot volcanoes like Hawaii or Iceland, and gives us those oceanic islands and occasionally continental flood basalts. If we look at a transparent mantle and crust, we can see a model for the D double prime layer. And here's the core of the Earth, and the D double prime layer is forming these plumes that rise up buoyantly through the mantle and erupt at the top of the crust as Hawaiian volcanoes, for example. A closer look at the D double prime layer shows that we have turbulent motion in the liquid outer core, and that there are convection cells that are coming down, so the colder mantle is denser and convecting downward. The mantle is getting heated up along the core mantle boundary and then rising up to form the source of those hotspot volcanoes and flood basalts. The asthenosphere is also convecting. It contains approximately 5% melt. That's a partial melt of the mantle asthenosphere, and so it's a basaltic melt. And the convection within the asthenosphere is helping to drive the tectonic plates. So we see those partially molten and convecting regions of the mantle where we get zones of upwelling at the mid-ocean ridges and downwelling of the colder asthenosphere that's been chilled by conduction from the cold lithosphere, and it gets subducted at subduction zones, and that denser, colder asthenosphere drops down, gets heated up again, and the cycle of convection continues. Here's a model of that mantle convection, and the red indicates hotter regions of the mantle, where you see these plumes originating at the core mantle boundary, rising up, forming a volcano. That mantle gets conductively cooled by the lithosphere and eventually subducts back down in these blue areas that represents colder mantle. So those are our mantle convection cells. Seismic tomography shows us considerable heterogeneity in the mantle, where we can see these subduction graveyards where lithosphere is dropping down into the deeper parts of the mantle when the subducting slab breaks off and sinks. And we also see these very deep plumes that are the origins of those flood basalts and hotspot plumes. And this also speaks to the fact that we can subduct crustal material, including continental sediments, into deep regions of the mantle. And we know that not only from the seismic tomography, but from different isotopes that have shown us that we have, for instance, sedimentary carbon isotopes brought back up in diamonds from kimberlite volcanoes. So we know that crustal material can be recycled into the deepest parts of the mantle. So there's a lot of mixing and a lot of heterogeneity in the mantle. This is another cartoon just to show these subduction graveyards and these mantle plumes originating at the D double prime layer, demonstrating to us again that we have a lot of heterogeneity and cycling with this convection that is mixing crustal and mantle material. Now, the crust that we have is all mantle derived from the early Earth, and the basalts that we get from partial melt of the mantle that are erupting in rift valleys like East African Rift, and that also start to open up oceans and become mid-ocean ridges and crystallize as oceanic basalts. That's the material that we started with, and it was mixing and partial melting and magmatic differentiation that formed the continental crust. Magmatic differentiation can proceed by many different processes. It is any process by which a magma is able to diversify and produce a magma or rock of a different composition. So here are some examples in this cartoon showing two different magma bodies mixing together. In the magma body on the left, we're seeing stoping or breaking off of pieces of the overlying host rock or the country rock surrounding the magma chamber. Those can be incorporated into the melt. We also see crystallization and crystal settling from the magma body itself. We see partial melting. These are two photos of rocks that show different stages of partial melting. On the right is a migmatite, and these essentially are felsic, high silica, high sodium, high aluminum, high potassium melts. So leucogranites are what they're called. These are sweats of this rock. It started out as sedimentary rock that was metamorphosed to conditions where melting started to happen. Melting began and gave us these sweats. It just got too hot and started to separate out these leucosomes. On the left, we have a migmatite that has gone farther and produced sills and dikes of this much more felsic material. These leucosomes from the the country rock from which it was derived, which looks much more mafic. There can be crystal fractionation. This might be a dominant mechanism for magmas to differentiate. We have crystals that form within the magmatic body that settle out, and we can see that in some cumulate rocks. And we see compositional differences as you go from the bottom of one cumulate layer to the top of that layer. This is also called gravity settling. We see evidence in the field for magma mingling or mixing. Mingling is where they're not mixing, but they are interfingering with each other. This photo shows pillow basalts accumulating at the bottom of a granitic magma chamber. And this is an example of mingling. If you were to see a mixture of the pillow basalts, of that basalt with the granitic magma, you would see something intermediate in composition. Here's some more magma mingling, what looks like there might be some mixing in these lighter or more felsic zones. We see assimilation or incorporation of wall rocks. These can be called xenoliths, so xeno meaning a foreign, like a xenophobe, lith meaning rock. It's a different composition. It's come from somewhere else. If you know that it is unrelated to the igneous rock that it fell into, then you can call it a xenolith. If you don't know its origin, but you see a strange rock within another igneous body, you can call it an enclave, a more generic term that doesn't suggest anything about the source of that rock. And it's by those magmatic differentiation or crustal processing events that we are able to go from the basaltic partial melts of the mantle to a more granodiorite or diorite composition that is the average composition of the continental crust. And so I have a list here of these kinds of processes: distinct melting events from different sources, various degrees of partial melting from the same source, crystal fractionation, mixing of two or more magmas, assimilation or contamination of magmas by crustal rocks, or liquid immiscibility. We looked at the average chemical compositions of the continental crust using different methods. You'll see that overall it's silica-rich with a lot of aluminum, not very much iron, more sodium and potassium compared to basaltic rocks. And I plotted those on a total alkali versus silica diagram, and these numbers correspond to these models 1 through 8. And I just wanted to point out that they fall mostly within the andesite field. They're also falling the trachyandesite field, and there's one, this outlier, number 8, that falls into the dacite field. So I think we can safely say overall our estimates for continental crust are andesite, and the plutonic companion to that might be a granodiorite or a diorite, somewhere in there.
that formed